So, scales. What is a scale? Now that we have units out of the way, as I've covered in the previous video, we must now see how to use said units. Because you could say that the room is 25 degrees Celsius, or that the volume of the water in a cup is 40 centimeters cubed, but what does that even mean? Why should it matter to anyone if the temperature of the room is 25 degrees Celsius, or 100 degrees Celsius, or negative 273 degrees Celsius? And well, dear viewer, here is where scales come in. A scale is defined as a set of numbers, amounts, etc., used to measure or compare the level of something. So, in other words, the numbers used to measure the intensity of a given thing. So, that's cool and all, but how does one actually go about setting a scale? Well, there's no clearly defined way in which to set a scale, but the general trend I've observed is that in order to make up a scale of any given property of matter, one must use one of two ways. The first consists of picking two measurements to serve as reference points. Typically, matter, as affected by something which you are trying to measure at a specific state, becomes 0 in the scale, and matter at a different state, much more affected by that which you are trying to measure, becomes some other number in the scale, normally 100. Now, I know all of this might seem confusing at first glance, so here's an example for this method. Take the Celsius temperature scale. Anders Celsius, when making the scale, chose 2 points in a substance in which it showed a visible change due to the temperature of the environment, and for this substance, he chose none other than the single most abundant compound on Earth, water. And as for the 2 points in which the substance changed, he chose the point in which water freezes and the point in which water boils to be his 2 points, 0 and 100 respectively. That way, 0 degrees Celsius is the point at which water freezes, and 100 degrees Celsius is the point at which water boils, and from that we can then make out the fractions which will become to be each degree Celsius. But it should be noted that apart from Celsius, there is also another scale which is widely used in physics to measure temperature, and if you're American, no, it's not the Fahrenheit scale. The one I'm talking about is, of course, none other than the Kelvin scale. By the way though, unlike Fahrenheit, the Kelvin scale doesn't drastically differ from that of Celsius. In fact, they're pretty much the same scale, the only difference between the two being where they begin. This statement might make you question why we even have both scales if they're both pretty much the same thing. The answer to that lies in the way the Kelvin scale came into fruition. The story goes that a long time ago, around the mid-1800s, this one guy named Lord Kelvin had a problem with the Celsius scale. Contrary to what you might think though, no, it wasn't because the measurements were all over the place as a result of the scale being based on a mixture of salt and water with base measurements at 30 and 90 instead of being multiples of the indices of 10, unlike other certain temperature scales. The big problem that Lord Kelvin saw in Celsius was in the fact that the scale had negative values. This was to be expected though, given as how temperatures which are lower than the minimum one required for water to freeze do exist. It was only natural for the Celsius scale to have negative values given its foundation. But whatever the case, this sat uneasily with Lord Kelvin, so much so that he set out to create a brand new temperature scale by finding the absolute lowest temperature physically possible and setting that as 0 for his scale. And so, Lord Kelvin began his quest, using the Celsius scale as a means to have some foundation with which to work. And after long, excruciating hours of hard work, he did eventually find what he was looking for. The absolute lowest temperature possible, which he found to be about negative 273 degrees Celsius. Once having achieved his goal, all that was left for him to do was to fulfill the other part of his mission, setting the temperature as 0 in his own scale. But that raised a question: what should he do in regards to the other values of the scale? And well, since he didn't really have any other thing to set as 100 in his scale, he just decided to stick with the Celsius scale for the rest of the measurements. Either that, he didn't want to inflict onto other people the suffering of having to convert not just from Celsius to Fahrenheit, but also to his own scale now, or he just thought that Celsius was a sound and reasonable scale and had no idea as to why he should mess with greatness and change it. Whatever the case, and whatever reasons Lord Kelvin had to do what he did, it stands true that he decided to incorporate the temperature scale which he worked with into his own new scale by having pretty much the same value for each of the units in this new scale. And that way, the Kelvin scale basically came to have the same values of the Celsius scale. But with the only difference being that the Kelvin scale is 273 values more than the Celsius scale. We can even see this in the formula which tells us how to convert Celsius to Kelvin, or vice versa. The temperature in Celsius is equal to the temperature in Kelvin plus 273. Now, we've already gone over how the scales for the metric system came to be, with a line running through Paris from the equator all the way to the North Pole. and we've also mentioned how eventually our definition for the meter evolved from a fraction of a given distance to the much more objective distance that light travels in a 299,792,792th of a second. But, as I'm sure you might imagine, the meter wasn't the only SI unit to be defined a certain way, only to change its description to a more objective one. Another measurement whose definition was changed to a universal constant rather than a human reference was time. The second, throughout the better part of the last century, was defined as 1/60th of 1/60th of a 24th of a 350th of the year 1900. This is because 60 seconds makes up 1 minute, 60 minutes 1 hour, 24 hours 1 day, and 365 days a year. So, in order to define the value of a second, just pick your favorite year and calculate the fraction corresponding to a second within that time frame. But, of course, we had to standardize that definition, so the scientific community had to pick a year to use in it, and out of all the years they could have possibly chosen, they chose the year 1900. And that was how a second was defined for a while. That is, until we found about the vibrations of a cesium atom. You see, it was found that the vibrations of a cesium atom are very reproducible, so much in fact, that you could precisely tell with very little error, if with any at all, how many vibrations of a cesium atom this fraction of the year 1900 lasts. And so, in order to make the definition of a second more reproducible and objective, it was decided to change the definition of a second from it being relative to the year 1900 to it being relative to the vibrations of a cesium atom. As it happens though, this had some really impactful ramifications, as by removing the part of the definition of a second which made it relative to the year 1900, or anything else the Earth was doing for that matter, and making it more objective, we were able to find out that the Earth's rotation was slowing down. Now, isn't that cool? This is something which is just insane to think about, and in the same way, this serves as a reminder of how the more objective our measurements become, the less susceptible to bias they are, and the more truth we can find about the world with them. Alright, now so far we've been talking about that one first method of figuring out a scale, that being picking 2 points and then having the units be fractions of the stuff within those points. But what about the second way in which you measure something? And well, for that method, you basically just choose what one unit of the scale would be equal to, and from there you just roll with it and determine your scale relative to that base unit you chose. Take the mole for example, the unit for the amount of a substance. A mole is defined as exactly 6.022140076 times 10 to the power of 23, or this number, of elementary titles in a substance. Now, elementary titles could range from molecules, atoms, ions, or whatever other types of particles you can think of. This is the other way of going about setting a scale, and as you can see, it results in a much more straightforward scale, as by choosing only one value to be your unit, you can then just measure how many of those values there are in order to get the units which correspond to what you're observing. In this case, how many elementary titles there are in a substance, or simply put, how many particles are present in said substance. And if you recall from the last video, there are other scales of measurements, such as the metric system, which make use of this method of setting a scale.